Hello and welcome. My name is Brenda Davison. This is SFU Math 152, Calculus 2. We are now going to cover section 5.5, the substitution rule. So a nice little problem here to try to prove. You could possibly do this by induction or perhaps find another method of doing this. So try it out. Doesn't matter if you solve it or not, but we're going to be in this course talking about adding stuff up, and this is a problem about adding stuff up. Okay, today what we're going to do is learn an extremely powerful technique for allowing us to figure out what is the integral or what is the antiderivative of a particular function. So we have some function, there it is, minus 2x e to the minus x squared, and we want to know what function has that derivative. And this method of substitution, of turning a harder problem into an easier one, is broadly applicable and very powerful. So we're going to go through how to do that for both indefinite and definite integrals. So we are here integrating with respect to x, and dx can be thought of as a differential. And were I to have a function that looks like this, u equals e to the minus x squared, I could ask what would be the differential du, and I'm asking that in terms of dx. So I would figure that out by taking the derivative. So right now I have a function u equals e to the minus x squared, and I'm going to take the derivative with respect to x on both sides. So that on the left-hand side is going to give me du by dx, and then I'm going to take the derivative with respect to x of e to the minus x squared. And that is going to give me minus 2x e to the minus x squared. Okay, so then I'm going to think then of du as being equal to minus 2x e to the minus x squared dx. So look at what's happened by making a substitution like this, making u equal to e to the minus x squared. I have then a differential du, which is minus 2x e to the minus x squared. So what I want to do is fully substitute this portion here, and I can see that actually what is sitting there is in fact just du. So my integral, this integral here, minus 2x e to the minus x squared dx, can be transformed into, with using this substitution, u is equal to e to the minus x squared, can be transformed into the integral of du, because in fact I found out that du is exactly this thing here. It is extremely easy for me to integrate du. The integral of du is simply u plus a constant. So then I know what is u because I made the substitution. U is e to the minus x squared, so I can simply write this then as e to the minus x squared plus c. And I have found the solution to the original integral. That was the integral of minus 2x e to the minus x squared dx is equal to e to the minus x squared plus c. Take the derivative and see if that's true. So I'm going to emphasize that again. Anytime you find an integral, you can always take the derivative and check whether you've done it right. Second thing I'm going to say here is this is not the only substitution I could have made. I could have made a different substitution, and I would enable me to get the same result. So the substitution that you use is not unique. You want it to be, however, simplify your problem, and part of being able to do this well is being clever about the type of substitution that you choose. So here's been a basic example. Let us look at a couple of rules, and then we are going to do a whole bunch of practice. Okay, the substitution rule, here it is. If u equals g of x is a differentiable function whose range is an interval I, and f is continuous in I, then we have a statement here of if the integral of f evaluated at g of x times g prime of x dx is the integral of f at evaluated at u du. Okay, so that is the basis of the substitution rule. Okay, you should be recognizing in here that what we're basically doing is undoing the chain rule. And in fact, that is how you prove the substitution rule. It is done by using the chain rule for differentiation, and in a sense it is a reversal of the chain rule. The substitution rule is saying that we can work with dx and du that appear after the symbols, after the integration symbol, as if they were differentials. All right, let us take a look at how to do this in a very practical sense. Find the following indefinite integrals. The integrals are indefinite because they have no upper or lower limit. Okay, answer is not obvious off the top. I don't think so anyways. Also, we had seen in the previous lecture that you might be able to expand. Clearly you could do that, but expanding a ninth power here is going to take you the binomial theorem and a whole pile of time to expand this all out. So that would take quite a bit of time. So the next thing that I'm seeing is that x squared is very nearly, so I'm looking at this portion here, I'm saying x squared is very nearly the derivative of this. So I get an idea that it might be a good idea to make a substitution u equals x cubed plus 5. Then I take the derivative and see what happens. That would be du by dx is equal to 3x squared. So I will then rewrite this like this. Du over 3 is equal to x squared dx. Now it's just algebra going down to that last step. Now, why did I do that? Because here I have x squared dx, and here I have x squared dx. So I can substitute x squared dx by du over 3 because they are equal. Meanwhile, here I have x cubed plus 5, and I can substitute that with u because u is equal to x cubed plus 5. So when I make a substitution, I have to substitute all parts of the integral, and I have to substitute them with things that are equal. That will not change my integral. So let me go ahead and do that now with the substitution I've identified. So this thing will be equal to the integral. X cubed plus 5 is u, and it's u to the 9. And x squared dx is du over 3. Now I have a way simpler problem. I'm going to integrate u to the 9 du over 3. That is equal to 1/3 u to the 10 over 10. I take the integral, take the derivative of that. I get 1/3 u to the 9 plus a constant. And then I back substitute. I know what u is. U is x cubed plus 5. So this integral then becomes equal to x cubed plus 5 to the 10 divided by 30 plus a constant. Okay, so now I have the answer to my original integral. If you don't believe that that is the answer to your original integral, no problem. Simply take the derivative of this and make sure that you get this. Okay, you could maybe even see that almost by inspection. So the key thing to do here is to look carefully for what would be a good substitution that will allow the problem to become simpler and make the integral into one that you can evaluate easily. Okay, let's try the next example. I see something underneath the square root sign. Maybe I don't see how to integrate that very easily. Yeah, but I also see that if I were to take the derivative of this, I'm simply going to get a constant. So I get the idea that maybe I should let u equal 3 minus 5t. Then what will happen is du will be equal to minus 5 dt. Okay, I'm gonna usually jump like this between these two steps, but what I am thinking here is taking the derivative of u with respect to t, and that is equal to the derivative of 3 is 0, and then the derivative of minus 5t is minus 5, and then I am multiplying the dt onto this side. That's how I got there. Du is minus 5 dt. Okay, which means, of course, with some basic algebra here, that dt is minus du over 5. Again, I'm going to make sure that I do a complete substitution. I've identified what is dt. So dt is d minus du over 5, and that is what has to be replaced right here. Those two things are going to replace one another. And then I have here, I have that this thing here is u. Okay, so I'm going to make a complete substitution. I'm going to substitute the entire thing, and I'm going to find that this integral, the original integral, is equal to the integral. Okay, so dt is minus du over 5, and so I have minus du over 5. Put that there. Usually I wouldn't probably do it quite so explicitly. I'd sort of put it together, but this is fine. And then I have 1 over the square root of u. Okay, I would likely want to write that like this, minus 1/5 the integral of du over square root u. Okay, now this is easy to do. I mean, 1 over square root u is u to the minus 1/2. So this 1 over square root u is u to the minus 1/2. So that will allow me to see how to use the power rule, and I can simply integrate this like this, minus 1/5 times 2 times u to the 1/2. Again, I'm sort of quickly differentiating in my head to make sure I don't make a mistake. It's easy to make the mistake with the constants. You forget the 2, or I don't know, you forget a minus sign. That's pretty easy to do. So it's always useful to sort of keep checking yourself as you're going. Okay, so that means then that the integral is minus 2/5, and what was u? I'm now back substituting. U was 3 minus 5t. And then I have the 1/2 there, and I have the plus the constant there. Okay, again, differentiate and check. You just got to do about 5 million of these things, and then and then it'll come quickly. Actually, I don't know how many that you have to do, quite a few, but the more that you do, the faster you are, of course, of seeing the substitution and going back and forth and checking. So, you know, do this as best you can. Now, also, once you've done a number of substitutions, you can start to sort of see how to incorporate the substitution without actually writing out all the steps. Let me just do that here. I'm like, okay, the integral of sine is cosine, so this is going to have to be cosine 3t. Oh, no, it's not quite cosine. I'm thinking the derivative of cosine is minus the sine, so okay, I need the minus sign. And then I imagine myself differentiating this, minus cosine of 3t, and I realize I'm going to get minus 3 sine of 3t. I don't want that 3, so I simply put the 3 here, and then I add the constant. So I can, in a sense, be doing the substitution in my head. And the substitution I'm sort of thinking of would be this: u equals 3t, du equals 3 dt. And that you can, why don't you try that out? Try that substitution, go through the procedure as I've done in the previous two, and then you should see that when you back substitute, you get back to that. So sometimes you can see it, sometimes you actually have to make the substitution to make things easier for yourself. Okay, here's one that's a little bit more complicated. We want to figure out what's the integral of du over u times the log of u squared. Okay, so what I'm looking for in a substitution, I'm looking for, let me substitute something, make something simpler, and then also can I see the derivative of my substitution also here? And also another, you know, sort of tip that you always want to do, you just think, I mean, just thinking about this right now, what about this? We don't know what that is, in fact, yet. Because of that, and because this is a difficult. Often when you're looking at a substitution, you want to substitute and get rid of the log function. So, and here I feel happy when I see that if I'm thinking, oh, gee, that log function there, I would like to see that disappear. And then I think, oh, look at that, 1 over u, that is the derivative of the log function. That makes things very nice for me. So those kind of two thoughts combined allow me to make the following substitution, or at least to try the following substitution. Now I'm going to have to use v, not u, because u is already used. So I'm going to say let v equal the log of u. And then that would mean that dv is equal to 1 over u du. Now I'm going to do a complete substitution on this thing here. That there's going to then be the integral, and 1 over u du is dv. And 1 over log u squared is 1 over v squared. Okay, so now I have something that's much easier. This is v to the minus 2, so I can easily integrate that, and I get minus 1 over v plus c. And then I back substitute, and that is minus 1 over log u plus c. Again, you can take the derivative. So I'm claiming this is the correct answer. Big message. I in fact really encourage you to try this just to practice. So message, differentiate and check. Okay. All right, so that is really that is it in a nutshell. We're going to do a couple of more practices. The skill really comes in having done enough so that you can quickly identify the substitution. And when we get other tactics of integration, you're going to want to understand, is this one where I should try substitution, or one whether I should try some other techniques? So you want to quickly recognize whether it's going to be amenable to a substitution, and having done lots of substitution makes that much easier. Okay, let's do another one. I'm looking at this sine of pi over v divided by v squared, and I'm thinking, okay, hang on a sec. If I consider what's the sine of pi over v, so I'm looking at this thing right here, right there, and then I think, okay, that's basically one, some number, but I'm thinking maybe 1 over v, and then I see that this is the derivative right here. 1 over v squared is effectively the derivative, or the lion's share of the derivative of 1 over v. So that leads me to the idea of making the following substitution. Let u equal pi over v, and then that will mean that du is equal to minus pi over v squared dv. And I'm looking at the integral, and I see, okay, I've got dv over v squared. So I'm going to move the minus pi to the other side. That will be then minus du over pi is dv over v squared. Okay, so now this becomes extremely easy. This is going to then be equal to the integral of sine of what? Well, pi over v is u, and dv over v squared is minus du over pi. That is not difficult to integrate. That is simply cos u over pi. Again, plus a constant. And then I differentiate cos u over pi. I see I would get minus sine u over pi. And that's exactly what I have under this integral right here. Then I back substitute, and I get cosine of pi over v divided by pi plus a constant. There we go. That's the answer to the original question. So differentiate and check and consider. So sometimes you'll try a substitution and it doesn't work. That's fine. You try it out. You go ahead and you're like, okay, I got something that is more complicated. I found that I couldn't really substitute very easily, etc., etc. You don't give up. You just say, okay, that wasn't my best idea. Let me try something else. Okay, there's some substitutions are more effective than others, and also there's some different substitutions that are equally as effective. Okay, so this one's a little bit trickier. Like I'm looking at this and I'm not seeing, you know, if I substitute 1 minus z, for example, and I look at the derivative of 1 minus z, I don't get z squared. If I substitute for z squared, I don't see myself really getting anything in the denominator. So this one's a bit tricky. So I'm going to show you a substitution that actually makes it simpler, but it's not so obvious. So this is what makes this kind of tricky, and there isn't an algorithmic way to do this. It's a bit more problem solving than differentiation, which is very algorithmic. Okay, so I'm going to, because I think having things a binomial underneath the square root sign is sometimes difficult. Like for example, I easily know how to integrate something that looks like that, but anything that looks like this is potentially harder, or something that looks like this is worse, possibly worse yet. Okay, and then, you know, possibly even more horrifying is something that looks like this. It becomes hard to understand, you know, if I'm, you know, sort of in order of how hard it is to integrate, this would be an increasing level of difficulty. So because I know that this is easier than this, I think of making the substitution u equals 1 minus z and seeing what happens. Maybe nothing good will happen, but I'm going to see. And that would mean that du is minus dz. Okay. All right, so I can substitute this away, and I can substitute this away. I cannot just forget about this though. So I need to understand what is z squared under this substitution. That's fine. I can do that. Here, this thing here, of course, implies that z is 1 minus u, and then that tells me that z squared is 1 minus u squared. Okay, now I can make a complete substitution. You must do a complete substitution. So this is equal to, if you don't make a complete substitution, this will go away and won't be equal, and that then the whole thing is lost. So the substitution must be complete. So okay, that's fine. Z squared is 1 minus u squared divided by the square root of 1 minus z, which is u, and then dz, which is minus du. Okay. Does it look better? I argue actually that it does. Let me write it this way, minus the integral of, and I'm going to expand this. That's going to be 1 minus 2u plus u squared divided by, and I'm going to write this like this, u to the 1/2 du. Okay, now I can actually divide this u to the 1/2 in the denominator. I can divide that into each one of these terms, producing something that I can easily integrate. So that's what I'm going to do in this next step. I'm going to divide that in. It's going to look like this, minus, and I'm still integrating, so I'm going to be here u to the minus the half. That's 1 divided by u to the half, minus 2u to the 1/2, and plus u to the 3/2 du. And then I will proceed to integrate each one of these things separately. All are now easy to do using the power rule. So I have here 2 u to the 1/2 minus 4/3 u to the 3/2 plus 2/5 u to the 5/2 plus the constant. Then I back substitute and I get 2, and then what is u? U is 1 minus z to the 1/2, and 4/3 1 minus z to the 3/2, back substituting each one of the terms, 2/5 1 minus z to the 5/2 plus the constant. Okay, clearly a much more difficult problem than the previous examples, and in fact you should check it by differentiation. And when you check it by differentiation, you're going to find that you have to form a common denominator and put them all back together to see whether you actually got what you expected. But that is the correct answer. So sometimes you have to kind of take a bit of a leap of faith, and you have to make a substitution without knowing, is this really going to get me what I want? Maybe I don't, I mean, better than sitting there doing nothing. So you make a substitution, you proceed, you're like, hey, actually, now this allows me to simplify the integrand in some manner, and then that allows me to integrate, and I can actually make some headway. So computers are ideal for computing integrals. Wolfram Alpha gives you easy access. Use it as a tool, but be warned, you have to do it yourself, and you will not be using Wolfram Alpha on quizzes and exams. Okay, so it's easy to do this. Wolfram Alpha, for example, say you wish to integrate this function here, x squared times x cubed plus 5 all to the power of 9. That's the one that we did earlier ourselves. And we did it differently than Wolfram. Looks like what Wolfram Alpha has done is here possibly expanded the thing out and then integrated term by term. You can actually ask Wolfram Alpha to show you the steps even. So there it is right there. There's our answer, and it does in fact show the exact substitution that we did, and we're going through like that. Okay, so you are encouraged, in fact, to check your answers with this. If you can't, if you're doing these on a homework, you can't make any progress, you could ask an integral calculator type of tool to do it for you and then show you what's going on and try to learn from that. Okay, but please don't do it where it's like, oh well, a computer can just do this, so I'm not going to bother to do it myself, because you need to learn how to use the tools that we're doing. And you'll have to do this, of course, on your own in an exam. That being said, one thing you should be asking yourself is, hey, how come the computer can do this? It must be some sort of an algorithm. Computers are not saying, no, they are not necessarily saying to themselves in a thinking manner, I wonder, should I do substitution or should I do something else, or what substitution should I use? How do I pick what to try? They have been programmed by a person to do a specific thing in a specific order, regardless of what the integrand is. So they have a certain amount of rules. Look at the integrand, do this, do this, do this, come up with an answer. So you should be asking yourself actually at this point, how is that possible? And unfortunately, in some sense, outside of some heuristic methods, the way that this is being done requires a lot more complex mathematics than we have right now. But we are now building the groundwork to be able to understand some of that higher level stuff, and then to be able to understand how this is happening. Okay, when I prepared this slide, or actually I don't know if I can't remember, perhaps even Jamie Mulholland prepared this slide. Wolfram Alpha allowed you to see the steps for free. Now I believe you have to pay a small amount to upgrade to Wolfram Pro if you want to see the actual steps. I don't think it costs very much, and if you're going to use it all the time, that's probably worth it. Okay, what happened? We've just done substitution on indefinite integrals. What happens if we're doing it on a definite integral? Okay, the only difference is that we must substitute the limits as well. So you notice it's the same rule, but you notice what's here is not A, and this is not B. This is G of A and G of B, where our substitution is u equals some function of x. We're going to use that same function to change the limits of integration. Okay, so when we make the substitution on an interval AB, then the interval that we are actually integrating on the u-axis becomes the closed interval G of A to G of B. Okay, please don't do this. This is wrong. Okay, you do the substitution all at once. As you move from here to here, as you move from here to here, these change, not in two steps, because this is actually not equal here, and it's also not equal here. So it is incorrect. So you want to just avoid this middle step, this very common thing to do. What you want to do is go directly substituting for the integrand and substituting the limits in one big step and ending up over here. Okay, that's what this statement is saying, telling you to do here. Let us do a couple of examples with the definite integral so we can see what I mean by making that done properly. So let's take a look. This is an easy integral here. This is the integral from pi to 2 pi of cosine, whoops, we've already seen the answer to this as well, at least for the indefinite integral. So let us just do a full substitution here, and and do it for the definite integral. So what we're going to do is we're going to say, okay, u equals 3t. That will be our substitution. Du is going to be 3 dt, so, such that du over 3 is equal to dt. Okay, then we take a look at the endpoints. I'm looking at this substitution and I'm saying, okay, when t equals pi, because this is here, t equals pi till t equals 2 pi. We don't normally write that, but that is what it means. T is going from pi to 2 pi because we're independent variable t. So when t is pi, I think, okay, that's fine. This t is pi. So what is u? That implies that u is 3 pi. And when t is 2 pi, that means that u is 6 pi. So now I go through and I make my substitution. The integral will be going from u equals 3 pi to u equals 6 pi. And the substitution on cos 3t will become cos u, because 3t is u, and the substitution on dt will be du over 3, because dt is du over 3. So I've substituted the whole thing. Okay, you don't need to back substitute. You're just gonna, now you proceed with the whole thing. We're coming out with a number, so there's no need for back substitution. It's a definite integral. We're coming out with a number. So we get now here 1/3. I integrate the cosine. I get the sine function. So that becomes sine u. Then I evaluate at 3 pi and at 6 pi. And that becomes 1/3 sine 6 pi minus sine 3 pi. And in fact, both those guys are 0. So the whole thing comes out to be 0. Okay, so I've gone through complete substitution, including the limits of integration. I integrate, I evaluate at the limits of integration, and I get a number. Okay, second example. Also a definite integral, the integral from e to e squared of log of u squared du over u. I need to make a substitution. I'm looking at the integrand. I see the log function. I'm almost always going to say I need to make some substitution to get rid of that little guy. Not only that, I see that same thing, du over u here. So I'm right away, I'm going to say this is a good idea. V is the log of u. That is the substitution I'm going to try to make. And then I see that dv is du over u. Now I am dealing with a definite integral. I've got limits of integration. So because u here is the independent variable. This is u is going from e to e squared. You do not have to write that on. I'm just trying to emphasize what's going on here. And then so I take a look. Okay, when u is equal to e, that means that v is equal to log of e, which is 1. And when u is equal to e squared, v is equal to log of e squared, which is 2. Okay. So now that I've seen if I make this substitution for v, what happens to the differential dv, and what happens to the limits of integration. I establish all that, and then I completely substitute. So then I say that this is equal to the integral. Now I'm thinking, what does v start at? V starts at 1, and it goes to 2. Okay, because when u is equal to e, v is equal to 1. Okay. When u is equal to e squared, v is equal to 2. I substitute here, log u is v, so this is v squared, and then du over u is dv. So this becomes 1/3 v cubed, evaluated at 1 and 2, and that is 1/3 times 2 cubed minus 1 cubed, and that is equal to 7 over 3. Answer. It's a definite integral. The answer will be a number. Okay. Similarly here, just a thing, you can use Wolfram Alpha to check your answer. So here's how you enter that. The little caret sign means to the power of. make sure you use brackets. So that means to the power of, and you enter integrate, you enter the function you want to integrate, and then you just say from, and then you say from u equals e to u equals e squared, and then it understands what you're saying. Nice thing is it translates what you typed into what it thinks the problem it's going to solve for you. Okay, so you can check if you make a mistake typing here and then you look at this, you're like, oh no, that's not the problem I wanted to solve. Then you can adjust your typing so that you see the problem that you wanted to solve. Also note that we may use ln, which this is usually what I do, ln, and I sometimes pronounce that ln, or ln, the natural logarithm. And on your calculator, you will see usually two buttons, ln and log. And this would be the natural logarithm, that's to the base e. And then this would be to the base 10. That's typical on calculators. However, Wolfram Alpha, and they tell you it's using the notation, and so do some textbooks. So you need to watch the context. That if you use log, that is the natural logarithm. Okay, so it has changed the ln to log. It's smart enough to know that, but it uses that notation. And then you can see that there's the answer, the same answer that we got. Okay, it gives you a visual representation. So you can check. I encourage you to do that. Okay, a couple of other niceties that allow you to do things quickly and without effort. I'm a big fan of that. That is even and odd functions. Even and odd functions can sometimes reduce the work down to nothing, and in other occasions have the amount of work. Okay, so let's just remember, what does it mean for a function to be odd? Here, an odd function, that means that f of x is equal to minus f of minus x. So, for example, sine is an odd function. X cubed is an odd function. Think about that. X cubed is odd. X cubed is odd. And you notice that this number is odd. That's not a coincidence. Okay, what does it mean for a function to be even? For a function to be even, it means that f of x equals f of minus x. Okay, for example, the cosine function is even, and for example, x squared or x to the 4 is even. Again, you'll notice that these things are even. That is also not a coincidence. Okay, if you are dealing with an odd function and you are integrating on a symmetric interval, that means that you are going from minus a to a. It's symmetric about the y-axis, then the integral will be 0. Okay, if you are integrating an even function and you're going on the same symmetric interval from a to a, symmetric about the y-axis, then that the integral will be twice the value of the integral on half the. So you can reduce this to 0 to a and put the 2 here. Okay, and this drawing is incomplete, so let's just extend this up. So what it's saying here, if I integrate here from, let us just say here, minus a to, let's try to go over the same distance, a, like that, it's saying that this thing here and this thing here are, those two integrals are equal and opposite and they cancel out. So the integral is 0. It doesn't actually, so long as I know that this guy is odd, that will always happen. Similarly here, if I'm going from minus a to, say here, a, I notice that this area is positive and this area is positive and they are both the same. So I could, in fact, just compute the area here and then multiply by 2. And that's what this statement here is saying. You can use this to reduce the amount of work. Reducing the amount of work is always good. Okay, so sometimes you'll see a very complicated situation in an exam that you should pause momentarily and think, okay, is there something slightly subtle here? For example, this function is odd on a symmetric interval, and I can now just write down that the answer is 0 rather than going through a huge ton of work on what looks to be a complicated situation. Okay, let's have a couple of examples. I'm going to try to integrate this. Okay, so now because I'm aware of this new fact, I'm looking here. I'm little go ding ding, right? Ding ding. A symmetric interval of integration. Maybe this won't help me out or, in this particular case, but maybe it will. So then I look, I see only even powers of x. So this is an even function, and I'm thinking of 4 as the function for x to the 0. Okay, so it's still an even power of x. So it's x 2x to the 4 plus 3x squared. So all the power plus 4x to the 0, all the powers on x are even. This is an even function. You could also check, does f of x equal minus equal f of minus x. That would be that's the condition for being even. How would I check that? Okay, f of x equals, well, that's the function itself, 2x to the 4 plus 3x squared plus 4. And then I compute f of minus x by doing a substitution, minus x to the 4 plus 3 times minus x squared plus 4. And I then see that this is a true statement. And I'm like, hey, look at that. That is, in fact, f of x. So f of minus x equals f of x. So therefore, this is an even function. So that means that this integral is 2 times the integral from 0 to 3 of 2x to the 4 plus 3x squared plus 4. And what have I gained? It's way easier to substitute in 0 when I am doing arithmetic. So I basically have the amount of arithmetic I'm going to have to do during this calculation. That makes me extremely happy. Okay, so I integrate. Let's not forget the differential there. I integrate here. Okay, and then I evaluate at 0 and 3. And evaluating all these things at 0 is super easy. They're all just 0. Now, if I had not done this, I would have to evaluate them all at 3 and all at minus 3. And then that's just a huge amount more arithmetic. So that's, now it's arithmetic. It becomes 2 times 2/5 3 to the 5th plus 3 cubed plus 4 times 3. Okay, you can use a calculator or plod through on this. I got 1362 over 5, which is 272.4. Okay, it's half the arithmetic. That's the point. Okay, now I look at this and I'm like, good gracious, what am I going to substitute? It looks just terrible. I see e to the minus u squared. I see a u squared plus 10 in the denominator. Not only that, there's a sine function. I am not seeing any reasonable substitution. And then I'm going to look here. I'm going to say, okay, hang on, let's be careful. This is a symmetric region of integration. Maybe I should try to consider whether this is an even or an odd function. Okay, so that's what I'm thinking. Is it even or is it odd? So let me just take a look then at the function. It's f of u is e to the minus u squared sine u over u squared plus 10. So some portions of it are even and some portions of it are odd. So this sine function is odd. This function here is even and this function is even. So I may know how to combine that or not. I mean, I'm saying that in the world of, it does not work like numbers. In the world of functions, if you have two odd functions, well, in the world of, so even times odd times even is odd. Okay, it's not even like it would be if there were numbers. So be careful. If that doesn't, if that's unsatisfactory, what then you can do is just check by saying, okay, let me see what is f of minus u. Well, that's going to be e to the minus u squared, right? Because I mean, minus u times minus u is u, so that isn't going to change. This is going to be sine of minus u, and then this is going to be u squared plus 10. But then what is sine of minus u? Sine of minus u is minus sine of u, so this becomes so this is equal to minus f of u. So I in fact can show, I showed now that f to the minus u is minus f of u. That's the condition of being odd. Okay, so just like roll back here. What does it mean to be odd? It means that f of x is minus f of minus x. That's what I've just shown. Okay, so I can either understand how to, I can either look at the parts and understand how to multiply them together. I think much safer is to go right from the definition of what it means to be odd and see whether that condition is satisfied. It is. This function is odd. This function, and by that I mean the whole thing here, this function is odd. Region of integration is symmetric about the y-axis. Therefore, the integral from minus e to e of this horrible thing here equals 0. No work required. Okay, so cautious of that. Like always be sort of trying to hold as many of the little pieces and facts in your head at a time. Always be on the lookout for little clues about what's happening to save yourself time and energy. Okay, that concludes the section on the substitution rule, a very important technique in integration. I will see you back shortly for the next lecture, section 5.6. Thank you.